All right, Gen Chem, we are going to talk about energy and change of state, and we're going to look at some energy diagrams, and then we are going to talk about some phase diagrams and learn how to read those as well. So today on these energy and change of state diagrams, we're going to really look at what it takes to change the phase of a substance. So let's talk about a couple of things first. I want to define heat, or the enthalpy of fusion. And we symbolize heat or enthalpy of fusion with this symbol, delta H fusion. That is, just gives us the heat of fusion. So here we go. Let's define it. It is the quantity of energy required Okay, so the quantity of energy required to melt a substance at its melting point. Okay, and we usually do the energy in terms of joules. And it's to melt a substance, and we usually have to do this by weight. So you'll find the units are joules per gram. Okay, so if the heat of fusion is the quantity of energy to melt something, what do you think the enthalpy or the heat of vaporization is? So heat of vaporization is done with this symbol. And it's the quantity of energy required to vaporize a substance. So the quantity of energy required to vaporize a substance. Oh my gosh, I can't spell. A substance at its boiling point. Okay? Once again, this is done in joules per gram. Okay? So let's look at this chart really quick. This chart, we are taking liquid water from negative 25 degrees all the way up to 25 degrees. So at negative 25 degrees, and we're in Celsius, by the way, that water is ice, right? So let's change color really quick. So if we're here at negative 25 degrees at point A, we are at ice. So A to B, we are ice. We are solid water. Now notice each of these hatch marks along the x-axis is more energy. So we are putting energy in as we go from left to right across this chart. Now notice all of a sudden at 0 degrees, our temperature doesn't go up anymore. Why is that? What happens to water at 0 degrees Celsius? Think about it. What happens at 0 degrees Celsius? That's our melting / freezing point, isn't that? So that's our melting / freezing point. So once I hit 0 degrees, that ice begins to melt. And it takes energy to melt. That's the heat of fusion right there. Okay? So all the energy that we put in there between B and C is actually breaking bonds of that crystalline ice structure, allowing those molecules, instead of to vibrate around little points, to actually flow and move past each other. So we're breaking down that crystalline structure. So between B and C, We are melting. And the energy is used to break the crystalline structure. And allow molecules to flow. Okay, so we're breaking down that crystalline structure, we're allowing the molecules to flow, and all that energy we're putting in between B and C goes to breaking down those bonds that hold it rigid in that crystalline solid structure. Okay, notice though, once all our water is melted, then we can actually start raising the temperature. So between C and D, we have liquid water. And once it's all liquid, then I can start heating up that water again. And then all of a sudden at D, our temperature doesn't change again. But we're putting in, look at all this energy that we're putting in. We're putting in so much energy, but that temperature isn't changing. What's going on? What is that energy being used for? What happens to water at 100 degrees? At 100 degrees, isn't this our boiling point? So what happens when something boils? We have liquid going to gas or vapor. We have vaporization. What does it take to vaporize? Those molecules have to, yes, they have to break all those individual intermolecular forces of all the neighboring molecules so that they can escape. That's a lot of energy to break the intermolecular forces. So between D and E, we are boiling. And the energy is used not to raise the temperature, but to break the intermolecular forces. So I'm going to shorten intermolecular forces to IMF. So the energy is used to break the intermolecular forces so the molecules can escape and vaporize. Okay, so notice how much energy it takes to vaporize something. It's a lot of energy. And then notice between E and F, once it's all gas, we can now raise the temperature of that gas. So between E and F, we have water vapor, which is gas. Okay, so I want to just point out something here. When a substance is melting or boiling points right here, adding more heat does not change that temperature. We've seen that here and here. It doesn't change the temperature of the substance until all of it has either melted or boiled. Then the temperature will rise. The whole entire system has to either melt or vaporize before we can raise the temperature of that system. Okay? All right, I've put a demo of boiling water in a paper cup because of this. This 100 degrees is lower than the flash point of paper, so I can boil water in a paper cup without burning the cup. It's a pretty cool demo. All right, let's go on to phase diagrams. So phase diagrams are really useful because we can see a whole range of pressures and temperatures where we can see the different phases of a substance, okay? So in this part of the phase diagram, we have our solid. So that's our solid. In this V-shaped part of the phase diagram, we have liquid. And on the far right, we have our gas section, okay? Notice between this line right here, we only have solid right here and gas. So this is our sublimation / deposition line. We don't even have liquid along these pressures and these temperatures. Only gas and solids are available to us at those pressures. Okay, along our y-axis, we have pressure. And pressure can be done in atmospheres, it can be done in millimeters of mercury, it can be done in pascals, all kinds of different units. And temperature along the x-axis. And we usually have temperature in Celsius. It usually doesn't, I've never seen one in Fahrenheit. That's really weird to see one in Fahrenheit. Okay, so let's look at this. I want to highlight a couple of things. So let's talk about point A here. Point A is called a triple point. And a triple point is a really unique spot, both pressure-wise and temperature-wise, where we have all three phases, solid, liquid, gas, all at equilibrium with each other. So it's the pressure and temperature where all three phases, solid, liquid, and gas, are found at the same time. In equilibrium. So if I was able to get a system down to 0.01 degrees Celsius and a pressure down to 0.006 atmospheres, I would be able to have solid water, ice, liquid water, and vapor all going. So I would have boiling, I would have condensing, I would have melting and freezing and subliming and depositing all going on at the same time. I've uploaded a video on this module for you so that you can see that. It's a really cool thing to see. Okay, let's look at B. B is what we call our normal freezing point. Now, what makes it normal is I'm at 1 atmosphere. Normal is 1 atmosphere. So this is our standard pressure. It can also be 760 millimeters of mercury. That's also standard, just a different way of measuring it. So normal, if you look at our normal freezing point, we're at 0. That's what we've always been taught, right? The freezing point of water is 0 degrees Celsius. Well, that's the normal point. Notice between A and D, this is my freezing line. So there's a whole bunch of pressures and temperatures that I can actually get water to freeze at. But we normally say 0 because that's normally the pressure that we have. Okay? All right, let's look at C right here. So C is my normal boiling point. Okay, now notice normal, once again, we're at standard pressure. And so once again, our temperature is 100 degrees. But notice between A and E, I have a whole bunch of different pressures and temperatures that water can boil at. So if I change that pressure, it's going to change the temperature that water will boil at. So when we say the normal boiling point, we mean 1 atmosphere or 760 millimeters of mercury, normal pressure. Okay? Let's look at D and E. So D is our critical pressure. That is the pressure that it takes to liquefy water, or a substance, I should say, a substance at the critical temperature. So this is the critical pressure. And E is our critical temperature. Notice anything higher than 379.99 degrees, that water can no longer be liquefied. It's just going to be vapor. So this is the temperature, the highest temperature, or actually this is E, the highest temp that a substance can still be liquefied. And we have to use the critical pressure to do that. Okay? If I go hotter than that, there's no way I can liquefy this. Okay, so let's answer these questions really quickly. What happens to the volume of water when it freezes? Have you guys ever froze something that's been in a bottle in the freezer, and then you opened up the freezer later and like the lids popped off the bottle, or heaven forbid the bottle's actually cracked because the water has frozen? Water expands as it freezes. Okay? It expands. That's why ice floats. Have you ever wondered why ice floats? Most solids are actually more dense than the liquid. They would actually sink, but water's really interesting. Water's the only thing I know of that actually expands when it freezes. So why do lakes and rivers freeze up on top first? Because ice is less dense than the water. So ice is less dense than the liquid water. That's why the ice freezes on top. Okay, this property is so unique. Water is the only common substance that does this. And it's one of the reasons that life is able to exist. Could you imagine if the rivers and the lakes actually froze like most normal things, where the ice would be at the bottom and they'd freeze from the bottom up? It would kill all the plants and animals and fish that live in the river or the lake. And every winter, every animal, every plant in that river or stream or lake would be dead. And we'd have to start all over. So that unique property allowed life to actually continue through the winter. Okay, so that is how you read phase diagrams. I just want to do a few more things. So what would happen? Let's get another color here, if I can find another color. What would happen if I started out, say here at 1 atmosphere and 200 some odd degrees, and I increased the pressure? If I increased the pressure here, I would go from the gas phase to the liquid phase. What would happen if I started out on that same point and I decreased the temperature? So if I decrease the temperature will go down. So if I do that, I would go from the gas, once again, to the liquid phase. Okay, so I'm going to ask you questions like this. Let's do another one. What if I started right here and I wanted to increase the temperature, I would go from the solid phase to the liquid phase. What if I wanted to decrease the pressure? I would go from the solid phase to the gas phase. I would sublime. Okay? So I'm going to ask you some questions like that as well. Just see if you can read the phase diagram and tell me what phase changes if I change temperature or pressure from a certain point. So good luck, have fun, and we'll talk to you later. Have a good day. Bye.